if you look at the properties, number one, I'd say they're capable of forming hydrogen bonds. They're aromatic, meaning they've got these conjugated double bonds and ring systems. So that's a bit of organic chemistry we may never thought of worrying about again, aromaticity. But that aromatic character leads to strong UV absorbance. And that's something we'll get to. You can use the absorbance in the ultraviolet like a 260 with a spectrophotometer to estimate how much DNA is in a sample. That's commonly done. But the downside of this aromaticity, it absorbs UV light. That means when you go out in the sun, your skin cells in particular are being blasted with UV rays. The DNA is being absorbed, the UV light's being absorbed by the nitrogenous bases. And what happens when a functional group, an aromatic ring structure absorbs a high energy UV photon? Some of the rings in the electron rings are, the electrons will be excited to an excited state from the ground state. It makes them more chemically reactive. You start cross-linking. Bad things happen.
Free radicals? Is that what
Well, it could cause it to actually eject the electron if it's energetic enough, but more likely it just goes to the first or second excited state in the orbitals, and that makes it more cross-reactive with neighbors. So, you know, that's the downside to using DNA as our genetic material. It's a kind of a fragile thing. And we have repair systems, which we won't go into. We have DNA repair systems that will kind of undo UV damage and other kinds of damage. It was in the news last week, if any of you paid attention to the awards, the Nobel